All right, in this lecture I'm going to go backwards just a little bit and talk about metric spaces. And the reason I say go backwards is because metric spaces is generally where you start when you study topology. And I don't know if that's actually true in all courses, but certainly the class I took in this subject a long time ago, we began with metric spaces. And then from metric spaces, we learned about open balls, right? Open balls, and then open sets, and then topologies. The problem, of course, is that this idea is actually the more fundamental idea. And in principle, I think the more modern approach is to start with topologies and work this way. But historically, it was developed this way. And the reason is metric spaces are reminiscent of geometry, because ultimately they are ideas that formalize the notion of distance for a set. Right? So if you have a set of things, right, a whole bunch of things inside a set, the things are just a bunch of collections of objects sitting inside the set. So anything that we add to it gives it some kind of structure. So far we've been, if this is the set X, we've given the set X a topology, the topology of X. That's something we endow to the set that gives the set a certain kind of structure, a topological structure. But the way I understand this actually happened, the first thing that they actually did is they tried to say, well, maybe we want to say that this element here in the set and that element there are close together, and this element here and this element here are far apart. Well, topologies can do that by things like the number of open sets that contain these things and whether those open sets are disjoint. But initially, the way to do this wasn't with topologies and open sets and separation axioms. It was with a thing called a metric. And a metric was a function that would take two elements of the set and give you a real number that would represent the distance between them. And it was sort of a metaphor for the plane, right? 2 points in the plane, there's always been a distance between them, right? Point X, point Y, there's a distance. And that distance is a function of X and Y, obviously. And we usually do this in terms of the coordinates of X or Y. So this notion of distance in geometry, it existed for a long time. The question is can you somehow import that notion of distance to any set? Can you create some sense of distance in a set? Literal distance, like a real number measuring the distance, not some abstract distance like we've been talking about with, say, the separation axioms of topology. So that was really where they started. The question is what does it take to create a notion of distance for an arbitrary set? And ultimately, that's what the concept of metric spaces was all about. So taking a literal metaphor for the plane, what they decided was that whatever this function should be, the distance between 2 points should equal 0 only when the 2 points are the same. Right? So that's sort of what if and only if, IFF. So the distance between x and y should equal 0 only if x equals y. Then the other obvious thing is that the distance between x and y has got to equal the distance between y and x. It's got to be symmetric, right? And of course, that's, again, literal metaphor with the plane. And then, let's see, what else did they want? The distance between x and y plus the distance between y and z must be greater than or equal to, I guess, the distance between x and z. This last one is called the triangle inequality. And you can see that that's super literal with the plane, right? Because any triangle you have, if the two of the sides are x and y, z is always going to be smaller than the sum of the two sides. So they wanted that. Oh yeah, and there's one other. The distance between x and y is greater than or equal to 0. There's no such thing as negative distances, right? So this was the original concept of a metric. It was like a literal transformation of the notions of planar geometry. And the question is now, can x and y be element of any set, right? And, you know, the answer is no. You can't just take any set and create a metric. There's certain theorems that tell you what sets can have a metric. Metrics define topologies, but metrics can also be built with topologies present. And there's a bunch of theorems about this, and they're called the metrization theorems. And they're pretty famous, and we're not going to do any of them. But not every set in every topological space can be given a metric. But if you do apply a metric to a set, you can always give the set something called the metric topology. The metric topology. And we've actually met the metric topology. We've called it the open ball topology. Or we've called it the usual topology when we're talking about the plane R2, the usual topology of R2. The basic idea of the metric topology is you define these things called open balls. And the open balls are located at a point x in the set, and they have a certain value of a real number r, and that's always going to be the set of all points in x is an element of x. I guess I should make that little x. This is little x, right? And little x is an element of our set, such that, well, wait a minute. It's going to be an open ball located, yeah, I guess that's the way it is. An open ball located at the point x, so I better do it this way, sorry. It's going to be all the points y are an element of x, such that the distance between y and x is less than r. Less than r, right? And that defines in the plane literally an open ball around the point x. It's all these points in here are the points y, such that the distance between y and x is less than r. So when we defined the open ball topology earlier on in this set of lectures, we implied the existence of a metric that would allow us to measure this distance r right here, right? Because without being able to measure distance r in the open ball, you can't really define an open ball. But if you have a metric that does allow you to do these things here, right, the metric that's defined in this way, then you can create the open ball. And then once you have the open ball, that becomes a basis for your topology. So this will become the basis of a topology. And that topology is the metric topology, the open ball topology, the usual topology. Now, if nobody says anything, they give you a set and a metric, you can pretty much assume that the topology on the space is going to be is going to imply that the topology on the space is the open ball topology. Right? If you have a metric, it really does imply this open ball topology. It's something that's kind of unspoken, but it's there. You can create other forms of topologies on spaces with metrics, but whenever we talk about the usual metric of Rn, we're always talking about the open ball topology in Rn, where the distance function, this distance function is given by the regular Euclidean distance, which, by the way, is always positive, obeys the triangle inequality, is symmetric, and is only 0 if x and y are equal. So it satisfies the requirements to be a metric, of course, because it's the literal foundational concept of what they invented metrics to be. But not all metrics, by the way, have to be like that. I guess I should point that out, right? For example, you could have a point here in the plane and a point here in the plane, and you could have a point here, a base point. And you could say that if this is x and this is y, we could say that the distance between x and y is actually this distance plus that distance, instead of just this distance here. And then the distance between, say, w and z is this distance plus that distance. So every distance goes through this point, this base, right? And it's like a train system, right? If you're in a city X and you want to get to Y, you got to take the train through, some big town like New York. You got to go to New York, and then you got to go out from New York. It's a hub, right? It's the hub distance, right? But then the same metric is okay if there's a city that's on the same line as you, say T. Well, in that case, the distance is just straight to T. You don't have to go to the hub and back. So in that case, the distance between X and T would actually just be the straight line distance as long as you're on the same line, right? So that's a metric, and that'll satisfy, you can check, that'll satisfy all the definitions of a metric. Another metric you could imagine is d of x and itself, or d of x and itself equals 0, but d of x and every other point y equals 1, right? Some sort of, if you're not yourself, you're always 1 unit away. So everything is equidistant away from everything else in the set, right? So that'll satisfy a metric too. And these will also satisfy open balls. You can make open balls out of stuff like this. They're a lot weirder, but nevertheless they are. So, so not all metrics have to be literally like the plane. And of course they can't be, because you're going to have different kinds of sets involved in all of this. But there's another important point to be really clear about here. So there's another important point to make about the usual topology, and that is that, let's look at Rn. Rn literally means R Cartesian product, R Cartesian product, R n times, where n is some finite number. Now, this whole concept of the open ball, if you look at just R, right, say we put 0 there, every point on R can be identified as literal, every real number can be identified as a point on the real line. This is called, say, the real continuum. Say the real continuum. And if I have a point, say, x, and I have a point y, I can define the interval, the open interval between x and y. I don't need to know this distance d. I don't need to know the distance between x and y to define this interval. All I need to know is x and y. So the open ball on just the real number line would be literally a point with a radius, and then I would take the radius on both sides, and I would call that a one-dimensional open ball. But likewise, I can define the exact same open ball if I just know this point A and this point B. So the point is, of all this, is that to define open balls on the real line alone, no metric is necessary. I do not need a metric to do this. If I have a metric, I could do it slightly differently, right? I could just choose R and a point. But if I don't have a metric, I still only need 2 points. I just need A and B, and I can still define exactly the same thing. So what's interesting is that if I talk about the real line, I don't need to automatically be talking about a metric if I'm talking about the usual topology of the real line. If I talk about the usual topology of the plane, things get a little bit more unclear, because literally speaking, the plane is R Cartesian R. And the natural idea when you see a Cartesian product, if nobody tells you anything, and you know that this is a topological space, R with the usual topology on R, which is, by the way, the topology where these things are the basis, right? The basis of open intervals, or which are open balls in one dimension. So I know both of these have their own topology. I know that R is going to have the natural topology on R squared. But the natural topology on R squared involves open balls. And if it involves open balls, it must involve radiuses. And if it involves radiuses, it must involve a metric, right? So, but the thing is I didn't give either of these. If I just invoked the idea that this doesn't have a metric and this doesn't have a metric, but when I form this, somehow this concept of a metric seems to pop into existence. But that's a bit of an illusion. It doesn't really happen that way. Because what's really going to go on is that we are going to always infer that R squared inherits the product topology. And we've talked about the product topology before, but basically the product of every open set in R square is going to be an element of this set, right? The Cartesian product of the two topologies, which are sets. Remember, topologies are sets. So I can take the Cartesian product of the two topologies and I get this thing. And what will happen is this guy here is an open interval, AB. This guy here, say, is an open interval, CD. And the these two sets will end up being this pairing, right? Remember, it's an ordered pair, so I'll go A, B, comma, C, D. Notice this is an ordered pair. This is a big ordered pair of open intervals. So I have an open interval here and an open interval there. And this open interval is inherited from this topology, and this open interval is inherited from that topology. This object is a member of the topology of the product topology of R squared. And it's actually, if you were to plot this in 2 dimensions, right, you would get a little box that goes from A to B and from C to D. And that would be, call it the box topology, where little boxes are the basis. These are open, by the way. I should make them open. Oops. These are open, so I should make them open with little dotted lines, right? And it's the box topology. So whenever I write down R squared, I'm really meaning that it's inheriting this box topology. And it inherits it directly from R, where no metric was defined. So there's no metric defined on R squared, but there's a pretty good topology. It's the box topology. But the fact is once you realize you have the box topology, compare that with the open ball topology. And what you'll realize without too much thought is that these two topologies, these two bases, if this is a basis for a topology, and this is a basis for a topology, the two bases actually make up the same topology. That is, every open ball can be built of an infinite number of open boxes, and every open box can be built of an infinite number of open balls. You know, you just cram those open balls smaller and smaller and smaller forever into the corners, and you put one box so that there's a corner basically at every edge of of the open ball, and if one basis can make another basis, if the two bases can make each other, then they can certainly make anything that can be made from the union and intersection of these guys and the union and intersection of these guys. The point is the box topology and the open ball topology for the plane R squared is the same, despite the fact that the open ball topology kind of implies the existence of this metric. But just because the box topology and the open ball topology are the same doesn't mean that you automatically get a metric for free. You have to actually write down a metric and apply it to the space as the mathematician involved. Right? These two spaces are different. R squared with the topology of R squared is different from R squared with the topology of R squared with a metric D. Right? And this is usually how things go with these sort of spaces. Everything that you actually endow the space with should be sort of listed as a grouping. And so these two spaces here, these are different spaces. And this one here is far more intricate and complex than this one here. However, these two topologies are in fact identical. So these sets, everything's identical except this one down here has the metric. And that's an important thing because a lot of this is inferred. So, I mean, a lot of times you'll just see R squared D, and the presumption in that case is that you're getting the topology inherited by the open ball topology on the metric. So that's just something to be aware of. But I want to point out that Rn, when we do all of our manifolds, right? Remember, we would have a set, and then it goes to a chart, and it goes to Rn, right? This Rn is Rn with the topology on Rn but there's no implied metric, right? There's no implied metric there. Unless you assign a metric, we're not implying that one exists. So that's why these are just coordinates ultimately, right? You can't measure distances here. You can only measure what the coordinates are. And this sort of maps these coordinates onto the manifold. All you're doing is finding the coordinates. The distances between things is actually determined by the metric on the manifold, which is a different metric, g mu nu. And that metric in special relativity and in general relativity is not the same as the metric we're talking about. Because this metric, right, remember g mu nu, if I take two elements of the vector spaces that we're dealing with, that can actually sometimes be less than or equal to 0. And sometimes when it's equal to 0, x does not equal y, right? So these metrics are pseudo-Riemannian metrics, right? And because of that, they behave very differently than the ones we're talking about in topology. So we can't afford to be confused with the metrics that are applied to space-time manifold, right? The metric tensor, which we'll talk about later, and the metrics we're talking about now, which are just metrics of topological spaces, which have all of these other rules here that these rules here that are not the same, right? This rule is totally gone in special and general relativity, and once that rule is gone, a lot of the other rules become, well, the symmetry rule is still there. That's good news, but this rule is gone too, right? Okay, so that is what the metric is. Now let's take the metric and study the metric topology and see how it makes contact, see how the concept of a metric makes contact with the abstract topology that we've learned about already. Okay, so now let's look at how the notion of continuity, and this and the metric are related. So we know that we already have a definition of continuity, and our definition of continuity is that given a space X with a topology and a space Y with a topology, that f, if it's a function from X to Y, is continuous if and only if the inverse of a region U is an element of the topology of X when U is an element of the topology of Y. And this is the definition of continuity we learned many lessons ago, and it is really the core definition, but it depends heavily on this abstract notion of a topological space, meaning you have a space with a topology. You have to have two spaces that are topologized. You have to have a function between them. And then if U is open in Y, which is the sort of the easy way of saying if U is an element of the topology of Y, then the pre-image of U under the function has to be open in X. And that is our go-to definition of what continuity is. However, there was a definition of continuity that existed before people really understood how to make a topology on a space. This abstract notion of a topologized space didn't exist. But what did exist was the notion of a metric. So now we look at how did they define continuity back then. And I shouldn't say back then. We still define it this way as well in certain courses in analysis, right, where you don't want to build the full architecture of topology just to define continuity. The point is they're equivalent, and that's what we're here to show. We're going to try to show that these things ultimately are equivalent under some circumstances. So now, instead of having a set with a topology, you have two sets with metrics, right? And this will be, so, the metric D is from X, Cartesian X to R, and the metric rho is from Y, Cartesian Y to R, right? So those are two metrics, and we assume that these things follow the basic tenets of what a metric is, those four principles. And then we have a function between them, so we're going to ask the same question. When is this function between X and Y, when is it continuous? And so the definition they settled on back then was the very famous epsilon delta analysis of continuity, which means that if I have 2 points, you know what, I'm going to use for my points little x and little y. 2 points, little x and little y, are in the domain, and therefore f of x and f of y are obviously in the range. And I want to be able to say that if these are metric spaces, that if I measure the distance between the image points, and I demand that those image points have a distance between them less than some arbitrary number epsilon, I need to always be able to find a distance between the domain points that is less than some number delta. So the basic principle being that if I squeeze the domain points below this number delta, I'm guaranteed that the range points will be below epsilon. But I can always choose epsilon to be as small as I wish, which means there's always a delta in the range, that if the distance between the 2 points in the domain, there's always a delta associated with the domain, such that if I make sure that the distance between x and y is below delta, I'll always be below epsilon. And this is true for any epsilon, right? It's true for all epsilon greater than 0, right? There exists a delta greater than 0. That's how the proof goes, right? You pick this one, and you prove that there always exists that one. And that is the definition of continuity based on the metric. And we want to understand, how do these two definitions connect? How does this connect with that, right? And the first problem to understand that connection is that these sets don't have a topology. All they have is a metric, right? So we have to say, well, in order to connect this with this, we have to understand a topology on these two sets. And we're going to give it the open ball topology. That's what makes this connection work. And in fact, ultimately, studying this very closely, people started realizing, there's this concept of open sets that seems to catch this very well. And then they realized, hey, those open sets, those are even more generalizable, and there's actually this concept of topologies. So what we're going to do is we're going to give these two sets the open ball topology, and now we are going to create x, t of x, d, and y, t of y, rho. And once you have the open ball topology, then you're going to see how these two definitions are the same. So what we want to, the proof, what we're after now to prove, is that given this, right, given these two sets, we want to show that f is continuous if and only if f inverse u is an element of the topology of x when u is an element of the topology of y. And by continuous, we're using the classic definition, which is the one we are talking, the epsilon delta, classic epsilon delta definition. So f will be continuous under the classic epsilon delta definition when this is true, if and only if this is true. And so the way we have to do that is we have to assume f is continuous and then prove this is true. And then we have to assume this is true and prove f is continuous, right? And it's not a very difficult proof. So we will let's go ahead and just begin it. We start by assuming f is continuous, and then we define the point x. That is going to be the pre-image, inside the pre-image of a set U, where U is an element of the topology of Y. So we decide that we're going to assume that we turn to Y and we look for an open set in Y, any open set in Y. And then that open set will have a preimage, right? And then we pick an X that's inside that preimage, right? There's no statements here. This is all set up. We pick an open set in Y and we choose X that's in the preimage of Y. So by assumption, U is open in Y. So we know that there exists another number, Z, such that rho of Y, Z is less than some number epsilon that we're going to pick. Now, how do we know this? We know this because U is an open set. And open sets contain neighborhoods of all their points. Right? So in the open ball topology, the neighborhood is a little open ball, right? So if that's the point, if this is the point Y, right there, and Y is sitting inside the open set U, we know that you can always make a neighborhood around Y in U because U is an open set by assumption. So every point in it, you can make a neighborhood. And in this case, we know that we can find a point Z in that neighborhood that is less than epsilon close to Y because we just pick any one of the neighborhoods of Y that's in U and we find a Z that's inside that neighborhood. And we say the radius of that neighborhood is epsilon because open balls are part of the topology, so they're open as well. So we always know that there exists a Z where that's true. Okay. Then our third step is F is continuous by assumption. Remember, we assumed that F was continuous. So F is continuous by assumption. So we know that there exists a delta greater than 0 such that the distance between X and some number W will be less than delta, and that therefore, if we choose that number delta, we know that the distance between Y, well, I should not jump to Y, that's a little confusing, F of X and F of W will be less than some number we can choose, and we will choose that to be the same number epsilon as we just chose, right? So F is continuous. So what's the definition of continuity? Well, if I take 2 points, X and W in the domain, I know that I can make the distance between the image of those 2 points less than epsilon, which is the same epsilon I chose up here, right? So it's the same, we're working sort of in the same neighborhood. And I can guarantee that those 2 points will be less than epsilon. I know that a delta exists such that I can find a W that's the distance between X and W is less than delta. Will guarantee that this is true. That's the definition of continuity, and we assume that F was continuous. So then I can conclude from that F of W is an element of U. Right? And that makes perfect sense because this open ball that we've described before around Y that contains a point Z, well, it also contains W. Somewhere in there is F of W. F of W is inside that same region, so therefore it's also inside U, right? So now I know that F of W is inside U. When, I should stipulate, of course, this is dependent on the fact that dx of W is less than delta, right? And so now I look at this thing, I look at that statement, and if f of w is less than u, then I can say that w is an element of the image of u, right? So I'm just sort of inverting this to say that w is an element of the inverse image of u whenever dx of w is less than delta. And then my last step is, well, wait a minute, let's look at this thing. When d of xw is less than delta, w is an element of the preimage. But look at how this is structured now. This means here that there's always, that whenever I can find this delta, or for any of these arbitrary, for these deltas, the distance between x and w is, if it's below delta, then I know that w is inside this set. Which means, but this is true for any w that's true, that is less than delta. And that defines an open ball, which means that every member of w, or every member of this preimage, there's a neighborhood around that point inside the preimage, which means the preimage is open, right? So that means that f inverse of u is open because it contains a neighborhood of every point. And so this is really the definition of open, right? And therefore what we've done is we've assumed that f was continuous, and we assumed that, and we started with an open set in the range space, and then we've proven that the image of that set is open, and therefore we've approved half the theorem. Now the other half, we start by assume that f inverse u is open when u is an element of the topology of y. If u is open in y, the preimage of u is open in x, and now we want to show that we want to show the converse. We want to show that f is continuous under the classical definition. So what we do is we start with the assumption, and then we build our open ball, and our open ball is going to look like this. It's going to be f of x with a radius of some little number epsilon. And remember, that open ball is the set of all points y that are in the range space, such that the metric distance between the image point of x and some point y in the range is less than epsilon. Right? That's sort of the definition of the open ball. So we take that open ball, and we know that this is an element of the topology of y by the fact that we've assigned the topology of y to have a basis of open balls. So by our assumption number one, I know that the inverse of this open ball, which I'll keep rewriting, I know that that is an element of the topology of x, and that's by assumption, right? Because I assumed this. So and I also know by assumption that since I know that x is an element of f inverse of the open ball, right? The same open ball. Because the reason I know that, of course, is that f of x is sort of defining the open ball. So this is the image of at least the range point, at least the image of x. So it's the pre-image of the image, so we know that X lies in the pre-image of the entire ball, obviously. That's not difficult or controversial. But now I've kind of put all of this together, and I'm going to say, I'm going to sort of basically invert everything, and I'm going to say, well, there exists a delta greater than 0, such that W is an element of the pre-image of the open ball, when the metric distance between X and W is less than delta. And this again is basically the definition of an open set containing a neighborhood of all of its points, right? This, if this is true, if the distance between X and W is less than delta, if this is an open set, I need to be able to find a delta that will give me a little neighborhood around X, right? And W is just going to be one point in that little neighborhood around X. And because this is an open set, it contains that neighborhood. So if W is in that neighborhood around X, that's very tight, that's contained in this pre-image of the ball, well, W is certainly also contained in the pre-image of the ball. So the way we can now invert that, and we can write that F of W is an element of the ball itself. Right? And once we know that F is an element of the ball itself, that implies that the metric distance in the range space between F of X and F of W is less than some number epsilon when d of X and W is less than delta. So in this case, remember, it's interesting here because we chose the delta first, and we're now concluding about the epsilon. But we know because this is open, right? We know that there's a neighborhood around that thing, but all of this only works when this is chosen. So when this condition, when these two conditions are met, well, it's guaranteed that the image point will be inside this open ball when the metric distance is less than delta, but the definition of being that open ball, because it's open, guarantees that the distance between the images is going to be less than epsilon. And of course, this is our classical definition of this is the classical definition of continuity. And so therefore, as before, we started with the converse assumption and we proved the classical assumption, whereas in the previous example we started with the classical assumption and we proved the abstract assumption. But remember, what's very key here is that we did decide that these topologies were the open ball topologies, right? That's important, right? Without that, you can't make conclusions about, you couldn't make this kind of conclusion, for example, in step 4. But anyway, the link between the two now is very clear. With the metric topology applied, the definitions of continuity are the same. And I focused on continuity because it's probably the most often cited and often used definition in the literature. If you are reading anything about manifolds or fiber bundles, they're always going to talk about continuous functions, or they'll talk about homeomorphisms. But homeomorphisms are just bicontinuous functions where f is continuous and f inverse is continuous. So this is that point of contact between the classical definition here and the abstract definition that we learned. As a bit of a further illustration, it's always interesting to think about closed sets as well. Right, and in order to sort of grasp what closed sets are all about, we want to understand the limits. Closed sets, we already know what closed sets are all about, but we need to know what closed sets are about in a metric, in sort of the metric classical sense. So to understand a limit, we think of a sequence of points, and we say they approach a limit x. So we have a sequence xn, which of course is going to be something like x0, x1, x2, forever and ever and ever. We'll call it x infinity. Countable sequence in it. And we say it approaches this limit x. Sometimes you'll say L. Matter of fact, why don't we do that? Why don't we say L instead? Xn approaches a limit L if the metric distance between xn and L can be made less than some arbitrary number. We'll call it, say, epsilon again. Whenever n, the index on this, is greater than some number n. So I can always find a value of n in this sequence such that the distance between the nth element of the sequence and L will be less than an arbitrary number epsilon whenever n is greater than, there's always some minimal n where the index is greater than that minimal n. This condition here will always be true. And all of these things with this metric definition is trying to squeeze things into something less than an arbitrary number, and then I can say that I make this arbitrarily small. That's what we mean by, essentially that's what we mean by the limit as something goes to 0. We're really talking about squeezing things into an arbitrarily small size. Because usually, when you set things equal to 0, or you're taking these limits, if you actually make it equal to 0, it doesn't make any sense. But if you make things arbitrarily small, you can prove very important things about infinitesimal mathematics. And that's basically what we're doing here. So we know that there exist these sequences that will approach a limit L. This is what we mean by that. This is what we mean by that. So the notion of a closed set now becomes, in this classical sense, that here's a set. I'll call it F. I can come up with all kinds of sequences in F, right? This is, say, these are a sequence of points, right? And the sequence can move around all I want, but if there's a limit to this sequence, if there's a point that this whole thing converges to, say that point there, then what I know is that I'll always be able to essentially draw a little ball around that point, and at some point every member of the sequence is going to be inside that ball, right? At some point, some index n, the entire sequence is going to fall inside that ball. Now, when you study this, sometimes the books just lay it out exactly the way I have, but others say, well, you can imagine some really crazy sequences out there, right? You can imagine a sequence that goes like this. x0 is here, x1 is here, x2 is here, but x3 and x1 are the same, right? So x3 goes there. Every odd one pops up to there, and only the even ones converge to a limit. Well, clearly, that's, no matter how big n is, you're never going to get that whole sequence inside an open ball around L. And so most topology textbooks or real analysis textbooks say, yeah, but every sequence has a subsequence that does this, right? So we forget these bizarre points. So a lot of times you'll see this discussion couched in the notion of a subsequence. So the choice is every sequence has a subsequence which behaves this way, or you have to say there exists a sequence that behaves this way. So different books take slightly different approaches. But anyway, the point of a closed set is that no matter what sequence you create, I'll use the subsequence language, no matter what sequence you create, if that sequence has a limit, if that subsequence has a limit, then that limit point must be part of the set F for the set F to be called closed. If the set F is closed, then every limit point is actually part of F. And this, of course, is exactly the kind of thing that we have talked about before about a set and its boundary, right? Here's a sequence that's totally inside F, but its limit is on the boundary, but the boundary is not a member, the boundary of F is not a subset of F. This is a symbol for the boundary of. And if that's the case, then L is not an element of F, and therefore this is not a closed set. It turns out the way I've drawn it, it's an open set under our topologies, but it doesn't have to be. We can imagine a set like this that contains its boundary everywhere but doesn't contain it there. And then here's a sequence that is not, that's not closed either. It's not open nor closed. So, so that's how you define closed sets using the notion of just metrics. A closed set is a set that contains every one of its limit points, and that means for arbitrary sequences inside the set. So now the idea closed sets, I guess I should say the complement of closed sets are open, right? And so that we have to kind of prove that the complement of any closed set contains a neighborhood of all of its points, which would mean it is open. So the way we think about this, of course, is we'll take our set, we'll call it F, and the complement, well, I guess the total space will be X with a metric D, and then everything other than F, which would sort of look like this, that's going to be X minus F, which is one way of writing the complement. Another way of writing the complement is X / F. Whoops, I don't think it's / actually. I think it's backslash. X / F, right? / is the quotient space, right? We did it that way for quotient spaces. I think backslash is a more common notation for the complement. Sometimes it would just be F complement. So all three of those notations are the complement of F. So assume that we'll call this, well, we'll call it FC. Assume that FC is not an element of the topology of X, right? Assume the complement is not open, right? And if that's the case, if the complement is not open using our notion of what open is, that means that there is some point in the complement, we'll call that point, I don't know, E. There's some point in the complement such that the open ball around E of size delta, right, that open ball intersection with F does not equal 0. Or I should say does not equal the null set. And that's true for all delta, right? Because if this complement were open, I would be able to take an element E in the complement, and I'd be able to find a delta such that there was a little ball that was entirely inside the complement. But I can't do that because it's not open. It's not open. That means there does exist an E where any open ball will not lie entirely in FC, and in fact, therefore, everything that's not FC is F. So that open ball must have, no matter how small delta is, a non-null intersection with F. But you can immediately see what that implies, right? If there's an open ball that, no matter what open ball you have around E, right? Imagine here's your point E, and here's your open ball of length size delta, right? But that always has a non-null intersection with F, no matter how small delta is. Well, you can easily see that if I'm in F over here, I can create a sequence that will approach E because I keep collapsing the open balls towards E. I can always squeeze this sequence right in to E. So E is definitely a limit point. E is a limit point of this sequent xn, but that sequent xn is in F, right? But by stipulation, E was an element of F complement, which means that E cannot be an element of F. But E is a limit point of a sequence in F. And we stipulated that F was closed, right? We stipulated that F was closed. So we stipulate that F is closed, which means it contains all its limit points. But then we stipulate that the complement of F, this thing here, was not open, which means this ball exists. And once that ball exists, which means this ball exists such that its intersection with F is always non-null, which means we can create this sequence which will always converge to E in F. But we stipulated that E was in F complement. It's a contradiction, therefore we must have been wrong somewhere, and the only thing that we could be wrong about, since we assumed that F was closed, and our next assumption after that was that its complement was not open, we assumed that this was our error, and that the complement is in fact open because of this contradiction. Now, likewise, we would have to prove the converse. So what is the converse? Well, I can sketch out what that proof would look like. Both of these proofs are basically little sketches. Now we imagine sort of the opposite. We want to show, see, we had our set F, then the complement of F was this thing, the way we kind of drew it. So I called this, what did I call it? F complement. So now we assume that F complement is open, right? This is the converse. F complement is open. All right, so now we take a sequence in F, right? So we take a sequence in F, and it approaches some value, say x. So xn is a subset of F, and xn approaches a limit, say L. I should not do x, I'll do L. Well, if so we assumed F is open. Well now if L is an element of the complement of F, right? If you can find a sequence where L is not a member of F, then L must be a member of the complement. But if it's a member of the complement, remember the complement is open, right? That's open. So that means that there's some ball around L that's entirely, so say this was L, right? Well, that means there's some ball around L that's entirely in the complement because the complement is open. But if that's the case, the sequence is entirely in F. So L can't be the limit, right? Because if the sequence is entirely in F, but there's an open ball that's entirely in the complement, then certainly the distance between some point in the sequence L is always going to be greater than delta, where delta would be the size of this open ball, at least, right? The size of the open ball. So if the limit of the sequence didn't exist in F, then, and the complement was open, then the limit couldn't be the limit. It's called absurd, right? We would say it's absurd. So therefore, our conclusion is that L is not an element of the complement. L must be an element of F. And that means for every sequence, the limit must be in F, which is the definition of closure. So that's how these, again, the metric comes into play here. The notion of the open ball topology and its merger with the metric comes into play here. So that, which is really the point of this whole thing, is just to show you that there's these other techniques that are used to discuss topology based on metrics, and they usually start and they make contact with our abstract notion through the ball. And a lot of time in real analysis books you see it. I also want to make sure that nobody gets diverted into studying these metrics as though they have something to do with general relativity. The connection is very, I mean, there is a connection, of course, but it's very, very awkward. So there's, of course, you could go on, and you could talk about compactness and paths and all kinds of things using metrics alone, but I think we've kind of exhausted the issue here. I just wanted to demonstrate this relationship.